recently we established the link between the eigenvalues of the system matrix and the stability properties of the system. Okay, and in our previous lecture we saw through a simple second order numerical example that one doesn't necessarily have to compute the eigenvalues to reach the conclusion that the system is exponentially stable. All one has to do, it turned out, that one has to look at the evolution of some carefully chosen positive definite function through the solutions of the system. Okay. Now, what we're going to do in this hour is we're going to formalize that simple but important observation to the so-called Lyapunov stability theorem. Okay. So we're studying internal stability, or stability in the sense of Lyapunov. Therefore, it's okay to consider, without loss of generality, the homogeneous differential equation x that equals ax. In other words, we can ignore, for our purposes, the B, C, and D matrices, okay, or the input and output considerations. Okay, consider the following LTI system: x dot equals ax, and this is an nth order system. Therefore, our state is a vector in Rn. Okay, so this is our differential equation. Now, regarding this system, we can make the following statements about exponential stability. The following 5 conditions are equivalent. Okay, and by equivalent we mean if one holds, then the any other also holds. Okay, first, the system x that equals ax is asymptotically stable. That is, all the solutions converge to the origin. Okay, 2, system 1 is exponentially stable. That is, the convergence is of exponential order. We discussed this earlier. That is, for an LTI system, these two things are equivalent. Okay, so whenever you have asymptotic stability, you automatically have exponential stability too, which is not the case for a linear time varying system or a nonlinear system. Okay, 3, all the eigenvalues of the system matrix have strictly negative parts. Okay, so all the eigenvalues are on the open left half complex plane. Negative real parts. Okay. Now, these first 3 statements we already talked about and in a sense proved using the behavior of e to the at state transition matrix and its relation to the eigenvalue locations of the A matrix, and that we did by the Jordan 4 arguments. And now what's new is the following 4th and 5th statements. Okay, so let me put 4 here. For each symmetric positive definite, we're talking about the real matrix, the matrix Q, okay, n by n, there exists a unique solution, there exists another symmetric positive definite matrix P which is of the same size with Q n by n, and remember n is the order of our system. To the following matrix equation, which, because it's important, has a name, and its name bears the name of its inventor. Okay, so it's called the Lyapunov equation. Lyapunov equation. ATP plus PA. Okay, now P is n by n. A, our system matrix, is n by n. Okay, so ATP and PA, they are two n by n matrices, and this equals minus Q. Okay, where Q is a positive definite matrix, where therefore minus Q is a negative definite matrix. Moreover, if you, for a given Q, if you solve that equation and find P, that P has to be symmetric and positive definite. Moreover, P is symmetric and a positive definite matrix. And 5 is the following. There exists a symmetric positive definite note. Remember this notation. A matrix greater than 0 means, for a symmetric matrix, that it's positive definite. Less than 0, this is the 0 matrix, means that it's a negative definite matrix. Okay? P greater than some other matrix means that you take the matrix to the other side, the difference is positive definite or negative definite, depending on the direction of the inequality. So there exists a symmetric positive definite matrix P for which the following Lyapunov matrix inequality holds. Lyapunov matrix inequality holds. ATP plus PA less than 0. And this means that this matrix here, n by n matrix, is, because of the notation, is a negative definite matrix. Okay. Now we're going to prove this important result, not because we don't believe the textbook and we need to be convinced, but we're going to prove it for two reasons, or at least two reasons. One of the reasons is that by looking at the proof, we will gain more insight on the meaning of these statements, okay, hopefully, which will make us better understand this stability theorem. The other reason for spending some time on the proof is that because the techniques that are used in a proof can be useful tools for proving later on other theorems. Okay, in fact, there are such techniques that they are in the proof. I'm not talking about just for this result, but in general, there are such techniques that they are more valuable than the theorems that they prove. Okay, because they can be used in many different, seemingly unrelated places. Okay, so let's begin our demonstration. Okay, the first three statements, or the equivalence of them, we already talked about, and in fact, in a sense, in an informal way, we proved it using the arguments on Jordan form, which allowed us to see the behavior of the state transition matrix and its link to the eigenvalue locations of A. Okay, so what we will therefore do in our proof is to show the link between this trio and the last two statements, 4 and 5. Okay, here we go. We have already established these equivalences. Okay, 1, 2, and 3, they all imply one another for our system x that equals ax. And this we did by Jordan form arguments. Okay, so what remains are the following. Okay, for instance, if we show that 2 implies 4, and then 4 implies 5, and then 5 implies 2. So if we can establish this cycle, since 2 is equivalent to both 1 and 3, we will have established everything is equivalent to everything else. Okay, so let's begin by the first implication. 2 implies 4. Okay, 2 implies 4. Okay, so our starting point is that the system is exponentially stable, okay, or e to the at. The state transition matrix is decaying exponentially, and from that we will try to show that this equation has a solution for any given Q, a symmetric positive definite matrix. Okay, now suppose that, okay, now we're assuming that the system is exponentially stable and we're given a symmetric positive definite matrix Q. Okay, so what we want to show is that the solution to this equation, P, satisfies the properties listed in the statement 4. So for a given Q, define the matrix P. Okay, this will be our solution candidate to the Lyapunov equation through this integral from 0 to infinity, and integrand is e to the a transpose t q e to the at dt. Okay, A is our system matrix, therefore e to the at is the state transition matrix corresponding to our system. Okay, for a given Q. Now, since this definition includes an integration through an infinite interval, we have to first make sure that this is a well-defined matrix P, or this integral can be computed, doesn't produce meaningless answers. So that's our first step. P is well-defined, that is, this integral for any Q produces something, some constant matrix, n by n matrix. Okay, the reason is that e to the at converges to 0 exponentially fast. Okay, because the system is exponentially stable. So we know that for such a system, it must be that the state transition matrix converges to 0 exponentially. So that's, and once we know that, so this is exponentially decaying to 0. This is not difficult to see that e to the a transpose t is also exponentially decaying to 0, and q is a constant matrix. Therefore, the whole integrand is exponentially decaying to 0. Therefore, even though the interval of integration is of infinite magnitude, this integral still produces something meaningful. Okay, so e to the a transpose t q e to the a t decays to 0 exponentially fast. Okay, and therefore the integral is well defined. Okay, so therefore this construction does produce some matrix P, okay, a real matrix. What remains to be shown is that that real matrix satisfies the equation. Furthermore, it's unique, symmetric, and positive definite. So there are lots of things to be shown. So let's begin with that P solves the Lyapunov equation. Okay, P solves ATP plus PA equals minus Q, the Lyapunov equation. Okay, so let's write ATP plus PA. Okay, now P is this. So ATP is, you multiply this integral from left by A transpose. Okay, A transpose is a constant matrix, therefore we can carry it inside the integration. And then you do a similar thing with this term. You multiply this integral with A from right. Okay, again, since A is constant, we can carry that inside the integration. And what we have is we have two integrations from 0 to infinity. And we can combine the two integrands and express that as a single integration. If you do that, this is what you obtain. A transpose e to the A transpose t q e to the a t plus a similar term e to the A transpose t q e to the a t a. Okay. Now this term is now our integrand. Now the key point here is to realize that this is the derivative of something, the integral, the integrand. So if you realize that it's the derivative of that something, therefore the integral will produce simply the thing of which this is the derivative. Okay, and that thing is e to the A transpose t q e to the a t. Okay, dt. Okay, so derivative of this is derivative of this times the whole thing plus this times the derivative of the second term e to the at. Okay, so derivative of e to the a transpose t is a transpose. Likewise, derivative of e to the at is a, and the derivative of this product simply is the integrand in the previous line. Okay, hence this integral produces e to the a transpose t q e to the at, evaluated from 0 to infinity. T goes to infinity and t equals 0. Okay, and this is what? Ln t goes to infinity, e to the a transpose t q e to the at minus e to the a transpose t q e to the at evaluated at t equals 0. Okay. Now, this produces what? Since the system is exponentially stable, it means state transition matrix e to the AT is converging to 0 exponentially. Likewise for e to the A transpose T. Therefore, this whole thing as T goes to infinity produces nothing. Okay, produces 0. As for this term, plug in T equals 0, by definition, the value of any state transition matrix at T equals 0 is identity matrix. Okay, so here what we have is identity times Q times identity, and that clearly equals Q. So what we have therefore is ATP plus PA equals 0 minus Q. Hence, the Lyapunov equation is solved by our candidate P. Okay, now we had some other claims in the fourth statement, such as that no other P solves that equation. In other words, the solution is unique. Furthermore, it was claimed that P is symmetric and positive definite. So let's also prove those statements or substatements. Okay, so we're still proving 2 implies 4. Now let's show P is symmetric and it's a positive definite matrix. Okay, to show P symmetric, all we have to do is we show that P transpose equals P. So by definition, so P transpose is the transpose of the integral, which is the transpose of the integrand integrated. In other words, we can write P transpose equals e to the A transpose T Q e to the A T transpose dt. Okay, so let's transpose this product that produces from 0 to infinity e to the A T transpose Q transpose e to the A transpose T transpose dt. Okay, and that yields from 0 to infinity. Now e to the AT transpose is e to the A transpose T, that is this transpose of the state transition matrix, e to the A transpose T, and Q transpose is Q because by definition we started with a symmetric positive definite Q, so that produces Q. And finally, the same argument here, this equals e to the A transpose T, which is e to the AT, e to the AT dt, and this is no other than our candidate P. Hence, P transpose equals P, and symmetry is proven. Okay. Hence, symmetry is established. Okay, to show that this matrix is positive definite requires a little bit of work. Okay, so what we do is the following. To show P is positive definite, what we do is we go to the very definition of positive definiteness of a matrix, and for that what we do is we choose an arbitrary but non-zero vector. Choose an arbitrary vector z in Rn. N is such that P is an n by n matrix, or n is the order of our system. Okay? And the only assumption that we make on z is that it's different than 0, but otherwise it's just an arbitrary vector. And by definition, if P is positive definite, then z transpose Pz must be a positive real number. Okay. So let's look at Z transpose PZ and try to say something about its sign. So that equals, so this is P, and then we multiply this integral from left and right by Z transpose and Z. Z is a constant vector, therefore we can put that inside the integration, and this is what we have then. Z transpose e to the A transpose T Q e to the AT Z dt. Okay, so that's Z transpose PZ. And let's write that as using a new notation. WT transpose QWT dt, where WT is this thing here. Okay, e to the AT times Z. In other words, W of t is the solution of our system x equals ax, starting from the non-zero initial condition Z. Okay, where W of t is defined as, or it represents e to the AT times Z. Okay, for future times. Now, since the matrix Q, which we started with, is a positive definite matrix, okay, when we look at the integrand, we have some vector transpose times Q times the same vector. So by definition, this thing here is never negative, okay, because Q is positive definite, okay. So since Q greater than 0, we have WT transpose Q WT is never negative for all times, okay. So which implies what? So here we have, so this is a scalar, okay, the integrand is a scalar, and it has this form. Q is a positive definite matrix, therefore the integrand is never negative. So you're integrating something that's never negative, therefore the result cannot be negative. Hence, Z transpose PZ is always greater than or equal to 0, which implies Z transpose PZ never being negative, okay. Okay, so this establishes that since Z was an arbitrary vector, this establishes at once that P is positive semi-definite, okay, but we want something that's stronger than that. We want to show that this is not only greater than or equal to 0, but it's strictly greater than 0, because Z is different than 0, and we want to show that P is positive definite, okay. So we have to go one step further, therefore. Also, Z transpose PZ has to be strictly positive, which implies that it cannot be 0, because otherwise we would have the following contradiction. Because if Z transpose PZ were 0, then we would have the following contradiction from 0 to infinity. WT transpose QWT dt. Okay, so that's our Z transpose PZ. And we want to figure out the implications of this guess, okay, that being equal to 0. And if we can reach contradiction, we will have obtained Z transpose PZ cannot be 0, and from this we will conclude that P has to be positive definite. Now, this implies what? This is something continuous, because W of t is the solution of a linear system, e to the AT times Z. This is scalar, it's continuous, and it's never negative, okay? And then you integrate that, and what you obtain is 0, from 0 to infinity. So that's only possible if this integrand is identically 0 for all times, okay? Because even if it's non-zero, even if it's positive for some time, that would produce, no matter how small, something non-zero on the right-hand side. But this integral produces 0, and that's only possible when this integrand is identically 0 for all times. Okay, so that implies W of t transpose Q W of t equals 0 for all times. Okay. So that implies W of t equals 0 for all times because Q is a positive definite matrix. Okay, meaning that this is 0 when W of t, okay, that vector is 0 by definition of positive definiteness. Okay, so what we have obtained is W of t equals 0 for all times. What was W of t? W of t was the solution of our system starting from the initial condition z. So if this is 0 for all times, so clearly it's 0 for t equals 0. At t equals 0, what we have is e to the at evaluated at t equals 0, which is identity matrix. So identity matrix times z, we have W of 0 equals z. Okay? Now, therefore z must be 0 because W of 0 equals z, but z cannot be the 0 vector. Okay? So that's a contradiction. Hence, z transpose pz cannot be 0. It must be a positive real number. Okay, so let me write what I just set down. But W of t equals e to the at times z. So that implies W of 0 equals e to the a times 0 times z. This is identity matrix by the property of the state transition matrix. Identity times z, that produces z. And z is different than 0. Okay? So here we have W of t different than 0, and here we have W of t equals 0. So clearly it cannot satisfy both, and we have to have a contradiction. Okay. Hence, to sum up, what we have achieved is z transpose pz for an arbitrary non-zero vector z produces a non-negative number, and furthermore z transpose pz cannot be 0, hence z transpose pz must be positive. Okay, z transpose pz must be positive for a non-zero z. And since we didn't make any assumptions on z was arbitrary other than that it's different than 0, it by definition implies that the matrix P is positive definite. Since z was arbitrary, we have to have that P is a positive definite matrix. Okay, so we're still proving 2 implies 4, and there's only one thing that remains now, and it's to show that this P is the unique solution to Lyapunov equation. P has to be unique. Okay. Now, we prove this using the same technique that we use here, namely the very powerful technique of contradiction. So we prove this by contradiction. Okay, so this is a statement, P is unique, and to prove it by contradiction, what we will do is we will assume that P is not unique. Okay, so there are at least two P's different from one another that simultaneously satisfy the Lyapunov's equation, and from that starting point we will have reached we will reach a contradiction, and that will be the way to prove, or one way to prove, that P is unique. Okay, so we suppose otherwise. Then there exists another P, let's call it P bar, and that's different from our candidate P, which we constructed through that integral, okay, such that both solves the Lyapunov equation, okay, namely AT P bar plus P bar A equals minus Q and equals minus Q. Now you subtract one of these equations from the other. Since the right hand sides are the same, in the new equation the right hand side will be 0 and the left hand side is AT P minus P bar plus P minus P bar A equals minus Q minus minus Q, which is 0. Okay, now note that d over dt e to the A transpose t P minus P bar e to the AT, okay, equals, okay, now if you differentiate this, what you have is derivative of this times the rest, and then derivative of this multiplying from right the rest, okay, like the chain rule generalized to the matrix case. And what you have is the following: e to the A transpose t times A transpose P minus P bar plus P minus P bar A e to the AT equals 0. Okay. Now, here we also use the fact that A transpose and e to the A transpose t, they commute with one another, and likewise A and e to the AT, they commute with one another. So what we did is we carried this A transpose here to the other side. Okay, now this thing here is 0. Okay, so this equals 0. And that means the derivative of this matrix here is 0. So that means even though we have time varying terms here, e to the A transpose t and e to the AT, this matrix must be a constant matrix. Okay, so e to the A transpose t P minus P bar e to the AT must be a constant matrix. For all times t greater than or equal to 0. And this constancy, combined with the fact that e to the AT goes to 0 as time goes to infinity, will give us what we want, namely a contradiction. Okay, so let's see how it goes. So that means e to the A transpose t P minus P bar e to the AT at any time t1 must equal e to the A transpose t P minus P bar e to the AT at any other time T2, okay? For T1, let's pick T equals 0. And for T2, let's choose something very, very large, namely infinity. Okay? Now, this produces, the left-hand side produces what? Plug in T equals 0, you have e to the at evaluated at T equals 0, namely the identity matrix. This 2 is the identity matrix at T equals 0. So identity here, identity here. Therefore, this whole term produces P minus P bar. How about this term here? E to the at is a state transition matrix. We're talking about an exponentially stable system, namely e to the at is converging to 0 exponentially fast. Likewise for e to the a transpose t, okay? This is exponentially decaying, that's exponentially decaying, this is constant, therefore the whole thing must be exponentially decaying. And at t equals infinity, this must equal 0. Hence, p minus p bar, this difference equals the 0 matrix, but that implies that those two matrices are equal. But we start with the assumption that they are different from one another. Hence, we have a contradiction, and hence P must indeed be unique. Okay. So that implies P equals P bar. A contradiction. Okay. Hence, with this last step, we have proven 2 implies 4. Namely, if a system x that equals ax is exponentially stable, then for any symmetric positive definite matrix Q, you can always find a P that solves the Lyapunov equation, which is ATP plus PA equals minus Q. Moreover, that P is symmetric positive definite, the solution, and it's unique. Okay. Hence, 2 implies 4 is established. Okay, now let's move on to the remaining steps. Okay, what we set out to prove was 2 implies 4, then 4 implies 5, and finally 5 implies 2. And now the next step seems to be 4 implies 5, but that's really obvious. Okay. And you'll see why it's obvious when you revisit these statements. So we're going to skip that. And then finally, we will try to show 5 implies 2. So 5 implies 2 is the following. Suppose that we had a P, symmetric positive definite matrix. And through that P, if you construct the matrix A transpose P plus PA, the new matrix that you obtain is negative definite. Okay, so that's a statement in P. If that Lyapunov inequality is satisfied, then we will have to establish the system is exponentially stable. Okay, final step 5 implies 2. So let Q be defined as minus A transpose P plus PA. Okay, now the statement of 5 was that there exists a P symmetric positive definite such that ATP plus PA is negative definite. Okay, if ATP plus PA is negative definite, then minus that matrix is positive definite, and that positive definite matrix we define as Q, our matrix Q. Now, given any solution of the system starting from any initial condition x of t of our system 1. Okay, x that equals ax. Define the scalar signal v of t as v of t x t transpose p xt. In our previous lecture, in our numerical example, we dealt with this v of t where p was the identity matrix. Therefore, we had the norm square of the solution. But this time, since we're proving the general case, we have, in a sense, a generalized norm square, and that can be constructed through this p. Remember that p is a symmetric positive definite matrix. Okay, now what we're going to do is we're going to look at the derivative of v of t. Okay, and we'll obtain something very important about that derivative due to the fact that ATP plus PA is a negative definite matrix. So let's see how. Then v dot, okay, time derivative of this scalar signal equals x dot transpose px plus x transpose px dot. Okay, simply we apply a chain rule here, and that equals x dot is ax. Therefore, x dot transpose is x transpose a transpose, and we have x transpose a transpose px plus x transpose p ax. Okay, and that can be written as x transpose ATP plus PAX. Okay, by x we mean the solution x of t. Okay, for simplicity we didn't write the t dependence, and that equals minus x transpose qx, because we define the matrix q as minus that ATP plus PA. Okay, now okay, so let's proceed as follows. V dot of t, okay, equals minus x t transpose q of xt. Okay, so we're starting from the line above, and that can be upper bounded by minus lambda min q. This is the smallest eigenvalue of q. Q is a positive definite matrix, therefore this is positive. Okay, but we have a minus sign in front, times the norm square of the solution. Okay, where we use the fact that x transpose qx can be upper bounded by lambda max of q times the norm square of x, and can be lower bounded by lambda min of q times norm square of x. So we are using the lower bound. This is larger than lambda min q norm square x. Okay, so you multiply both sides with -1, and then what we have is this is less than or equal to that, because after that multiplication the inequality changes direction. Anyway, so to go to the next step, we will use the upper bound, and we can write lambda min q over lambda max p x t transpose p xt. Okay, where we use the fact that lambda max p norm square x upper bounds x transpose px. Okay, so using this inequality we can re-express minus norm square of x of t, and that produces this, and this equals minus alpha. Now we combine this ratio. This is something positive, this is also something positive, because p is a positive definite matrix. The ratio, so this thing is positive, and we're calling it alpha. Okay, and we have a minus sign in front, so we have minus alpha times x transpose p x. And x transpose px is no other than our scalar signal, v. Okay, v of t, where we defined alpha as lambda min q over lambda max p. Since both numbers are positive, because p and q are positive definite matrices, this alpha is, it could be something small, but nevertheless it must be positive. Okay, so what we have obtained is v dot, and v is a scalar signal, don't forget, that's the whole beauty of it. This scalar signal's time derivative is less than, okay, or equal to minus some alpha times the value of v, okay, at that particular time. Okay, so if this was an equality, v dot equals minus alpha vt, we will be able to directly write the solution of v of t. v of t equals e to the minus alpha t times v0. But it's not an equality, it's a differential inequality. So we have to be just a little bit careful, but the result is not surprising. And for that, we can use the comparison lemma. Okay, it's more or less obvious, but for the sake of completeness, because this is one of our most important theorems in this course, let's also go through the comparison lemma. Okay, so here we have a small digression from our proof, because we need a lemma to complete our demonstration, and that lemma is called comparison lemma, which says that if you have the following first order differential inequality, v dot less than or equal to minus alpha v, then, and v is something positive, then that implies the solution, no matter what it is, must be upper bounded by e to the minus alpha t times v0. Okay, so let's prove the comparison lemma. So define another scalar signal, w of t. Define w of t as e to the alpha t times v of t. Okay, and then compute its time derivative. Okay, w dot equals derivative of this times the whole thing times this, and this times the derivative of v. So what we have is alpha e to the alpha t v plus e to the alpha t times v dot. Okay, and v dot is less than or equal to minus alpha v, so here we can write alpha e to the alpha t v minus e to the alpha t alpha v. Okay, note that this term and that term, they are equal to one another, therefore the difference is 0. So what we have obtained is this newly introduced scalar signal w of t is such that its derivative v dot is less than or equal to 0. That means its derivative is never positive, hence w, that signal, whatever it is, it can never increase. Okay, it may stay constant or it may decrease, but it can never increase. So that implies w of t, however it evolves, can never become larger than its initial value. Okay, w of 0. Okay, once again, that's because w of t, w dot is less than or equal to 0. Okay, its derivative can never be positive. Now, what's w of 0? Plug in t equals 0 here. This is 1, and we have v of 0. So here, this equals v of 0. And then we replace w of t by this right-hand side, and what we have is e to the alpha t times vt less than or equal to v of 0, e to the alpha t V of t less than or equal to V of 0. And then we take this guy to the other side. Since it's a positive number, the sign of the inequality will, the direction of the inequality will not change, and we have, therefore, V of t less than or equal to e to the minus alpha t v0. Okay, so that's the proof of our comparison lemma. With this lemma in our hands, now we can proceed with our proof. And where we left was w of t less than or equal to minus alpha, excuse me, v dot, okay, of t less than or equal to minus alpha v of t. And by comparison lemma, we now know that v of t must be less than or equal to that. Okay, and v of t is here, x transpose px. Now we're wrapping up. Therefore, norm of x of t square, okay, less than or equal to 1 over lambda min p x t transpose p x of t. Okay, so we use the lower bound on x transpose px in terms of its eigenvalues, and the norm square of x. This thing here is what we define as v of t, and v of t is less than or equal to minus e to the minus alpha t times the initial v, e to the minus alpha t times v0, and here we have lambda min p, and here we have x0 transpose px0. This is our initial v, v0. Okay. Again, using the upper bound, once again we can write lambda max p over lambda min p e to the minus alpha t. Okay, so we're upper bounding this by lambda max p times the norm square of x0. x0 norm square. Okay. Here we have the norm square of x of t, and here we have the norm square of initial state. Therefore, all that remains is to take the square root of both sides, and we have the following. Norm of the solution less than or equal to lambda max p over lambda min p square rooted e to the minus alpha over 2t, and then we have the norm of the initial condition. Okay. Remember that the definition of exponential stability is such that whether we can find a k and lambda both positive, such that all solutions, norm of all solutions, are less than or equal to k times e to the minus lambda t times the norm of the initial condition. Okay, so with this being k and alpha over 2 being our lambda, we have exponential stability directly from the definition. Okay, exponential stability, and that completes our proof of Lyapunov's stability theorem for LTI systems.